the second episode on the fixed point representations. And in this episode, we'll cover various topics and examples. So let's get started. Now we'll talk about the binary representations of fixed point. So as we had covered in the previous episode, the binary representation now boils down to a sign bit and some magnitude bits, except because we're talking about two's complement representation, which is the most natural for the computer, the meaning of these bits is as follows. The lowest bit is obviously as binary numbers go to the power 0, to the power 1, to power 2, to power 3, but the sign bit has that same thing, which here is the fourth bit, so it's 2 to the power 4, but with a negative. So if this bit is a 1, then it carries with it a weight of minus 2 to the power 4, right? So that is the representation. Now you can take um, another way of looking at it would be if you are given um, a number, and if you want to convert it to its negative, let's say this is a positive number, which is 1, and if you want to convert it to negative, then what you would do is you would invert this, and we covered this in the previous episode. This is just a recap that you just have to invert all the bits and then add a 1. And if you do that, then you get this number, and this number is basically uh, minus, or this is 31, and 31 is a minus 1. So we know that the way to convert a positive number to its equivalent negative number or minus of plus 1 is done by inverting every bit and adding a plus 1. So this is the method by which you can do this conversion, but we've already talked about it. This is the representation. If a number is given, you can come up with its value by this method, and the value is going to be basically these these representations like a minus 1, minus 2, and so on, right? Its physical representations may look like this, like a 31 written here as 31 would actually come up to be a minus 1. So I think this is basically a quick recap of what we discovered last time. Next, we dive into the sizes. So how many bits does it take to represent a number? And the way we do this is by looking at the positive magnitude. In this case, the positive magnitude goes up to 15, and we know 15 takes 4 bits. And so you're going to take 4 bits for magnitude and 1 bit for sign. So basically, this would be a 5-bit number, right? Because 15 was the highest positive number. We know 1111 is representation of 15, so 4 bits plus 1. And that's how many bits does it take to represent a fully signed number where 15 is the highest magnitude. Now, the next topic is going to be how are fractions represented in this system? Because so far we talked about integers, right? And when we talk about fractions, we know that a number like 2.5 would have zero point 0.5 as its fractional. And what does 2.5 mean? 2.5 means 2 plus 0.5. So in the normal decimal system, it works like that. In the binary representation or fixed point representation, it could it's slightly different, so we'll cover that in a second. But we already covered the integer part. So integer part in this case, if it's a 3.2 representation from 3 bits here, dot 2 bits for the fractionals. If you think of this number like this, one way to do the math on this is to just remove this decimal point and do the math on the 5-digit integer. It's almost like you're doing math on 5-digit integer, right? So that's, and then afterwards you can place the dot in the appropriate location. But that's the easy part, that when you do these fractions, even the fractions could be added like just a regular integer math. So that's the simplification. Now, if you just look at this conversion, um, the way 0.5 works is that the representation after this decimal is to the power minus 1, to the power minus 2, and so on and so forth, right? All the bits are added up like that. So this is 1/2, 1 over 1/4, 1/8, and so on, right? So these bits get added like that. On the integer side, it's the same as usual, 2 to the power 0, 2 to the power 1. And because this is a sign bit, it's negative 2 to the power 2 if it's a 3-bit. So in this case, this represents 2.5, like here, right? So this is easy to see. Now, if you come up with negative numbers, it's a little bit more complicated because in binary number system or this fixed point number system, the part in the fractionals is always positive. In decimal system, minus 2.5 is written as minus 2 plus minus zero point 0.5, right? So that's minus 2.5. In case of binary, this decimal part is always positive. It's not negative. So if you want to represent minus 2.5, the way you would represent is minus 3 plus 0.5. So you have to represent 3 here, which is, sorry, minus 3 here. And so if you see this minus, so this is minus 4 plus 1, that's minus 3, and then, you know, zero point 0.5 here. So this is minus 3 plus zero point 0.5, and this becomes minus 2.5. So important representation, if you want to pause here for a second and take a look at it again, make sure you understand this. The important thing is that the fractional part is always positive. So you have to convert your integer part by doing a minus 1 accordingly, and then adding a plus 1 so that your fraction here converts to a positive fraction, right? This part is very critical. So make sure you are on board with this. Next, we talk about an important topic, overflow. When we start to do math on the fixed point numbers, the numbers can grow in size and in number of bits. And then you will encounter overflow. So if you do your math incorrectly without sizing um, the sum or the multiplication correctly, you'll end up with the wrong result, and we don't want that. So what is overflow? Let's take an example of adding two numbers. When you add two n-bit numbers, the result can be n plus 1 bits, right? So to do this binary math, we must expand the number of bits or detect and truncate. There are two solutions. And both of these will work with different results, but they are both acceptable solutions. One, you can start with the exact number of bits that you need and plan for it. The other, you know that you don't have those many bits or you don't want to spend those many bits. So you will detect that an overflow has happened and truncate the solution, right? So let's take an example. If you do 15 plus 15, we know that for this 5-bit signed number, 15 is the highest positive number. So if you add 15 plus 15, it becomes 30. And if you look at this is 15 in a 5-bit number, this is 15. I get this, which is the 30. And the 30, the MSB is a 1, right? So what has happened? What has happened is that I started with two positive numbers. When I added them, my sign bit flipped. And why did it flip? Because there was an overflow, right? Because my magnitude has now flowed into the sign, which shouldn't have happened. So when this happens, the sign bit flips when you add two very large positive numbers or two very large negative numbers, the sign bit will reverse. If you add two negative numbers, it'll become a positive number. Or if you add two positive numbers, it became a negative number. This is a sign that an overflow has occurred. Either side is the same. If you add two very large negative numbers and this became a 0, then that's an overflow. And if you add two positive numbers, then it also can happen. If you do a positive and a negative, it should never happen because you will stay within this space. It's only when you add two positive numbers or two negative numbers, that's where this overflow happens. So the sign bit has reversed, and the first solution is expand the number of bits. So instead of adding 15 plus 15 in 5-bit, you do this math in 6-bit, and you just sign extend it. And if you sign extend it, then these numbers become like 6-bit, where 5 digit is the magnitude. And if you sum them up, this bit has reversed, but now it's just a magnitude bit. It's not a sign bit, so it's okay. Plus 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 remains a plus, right? So it's great. This works. Just use an extra bit on every um, you know input, and then the solution will have an extra bit. So this works. Now the other alternative is to truncate. And how do we truncate? Simply, if you add 15 plus 15 and you detect that this bit has flipped, positive plus positive has become negative, just detect this. And then what you would do in the truncation part is that you basically say, if I do this and if this flips, then I'm going to put the largest positive. If these are two positive numbers and I turn negative, then I'm just going to put the largest possible positive number, which was plus 15. I'm just going to truncate to that. I don't care if it's larger than that. I just saturate. Same thing happened on the negative side. And this is just an example. If you add two 15s on the negative scale, you get minus 30. and so it flips. You see that it became positive. Two negatives became a positive. You basically saturate it to the largest negative, right? And that would be the answer. So um, you basically saturate to minus 15, and which should have been 17 here. So so yeah, I think that this is incorrect. It should probably be like, you know, it should be minus 16 maybe, right? Because the largest negative number is is um, is minus 16. So I think there is a little bit of error here, but you get the point. I guess if you go two negative numbers, then if you detect that an overflow has occurred here, then you just need to replace it with the largest negative number, whatever. In this case, it should be minus 16. So I need to correct this. I think in this case, this is wrong and it should be minus 16. And here, it's the same thing. It's basically minus 16. And minus 16 should be just what? It should be 0, 0, 0, 0, 1, 4, 8, 16. Yeah, there you go. So this bit would be a 1, right? So um, so that's, I think, the case here. And so this is the plan B, which is, if you don't want to add an extra bit, you have to, whenever you add two numbers, um, basically you have to truncate it if it gets too large. Same thing holds for multiply. The overflow can happen in multiplication because 15 times 3 is 45, which is too large. It's way larger than 15. So if this overflow happens, what do we do? Right? So in case of multiplication, when you multiply an n-bit number with an m-bit number, the solution is going to be, and these are obviously signed numbers, right? So n-bit means one sign and n minus one. This is one sign plus m minus one. Obviously, the solution is going to be one sign and n plus m minus two, which is total of n plus m minus one bit number. And so what we need to do is that before we multiply this, we sign extend both of these numbers to n plus m minus one. Then we multiply like regular numbers. The answer should be correct. You will not get wrong answer. So the important thing was to know how many bits it'll end up with, sign extend everything in that, and then multiply them like regular numbers. It should work just fine. Here's an example. If you take 45 and if you extend it, um, then you should really start using 9 bits. And if you multiply 15 and 3, you get 45, which is the right answer. If you multiply negative numbers, the same thing, just use 9 bits and sign extend. Sign extending negative numbers looks like a bunch of ones extended here, but once you do that, you get the right answer, which is negative 45. You can obviously pause here and make sure you do the math yourself. But once you sign extend, the math is just straightforward. The multiplication is just straightforward. Okay, so in this slide, we're going to talk about all that we have learned and applied so far. And what we have essentially learned is that we know how to multiply numbers, and then when we sum them, um, and we want to sum them, maybe there is a bias involved here as well. Um, and then we want to apply this activation function, so on. So this is the whole neural network perspective. And if you want to implement a neural network, we have to do fixed point multiply. And if you know this is, n-bit number, and if you know this is m-bit number, then you know that this multiplication is n plus m minus 1 bits. And if you sum them, all these, every time you sum them, you could increase by a bit, right? So you may want to truncate them when you sum them up, so you stay with this size. If you do that, you basically have to detect and truncate overflows and stay at this size. For example, you may want to keep, if this is, 2 plus, let's say, 5 bits, 5 fractionals, 2 integers, and this is 2 plus 5, then you may want to keep this where the sum remains at 2 plus 5 or something like that. So you want to basically detect overflow and stay at 2 plus 5. And then Same thing here. When you sum it with the bias, you may want to stay with 2 plus 5, and then your activation function will basically work off of that fixed point. So in a sense, what we have applied here is the concept that fixed point math is effectively capable of implementing this complex machine learning neuron without much difficulty. The only question is it accurate enough compared to the floating point without using all the bits, like every number is represented by a 32-bit value? I don't think that's needed. I think you can probably run both examples and see which one gives you better results. Um, Obviously, it's going to be floating point, but if your fixed point results are close enough, sometimes they're off by a few percentage points, and that's probably good enough where your detection result is not going to vary with that much error. And if that's the case, why not go for? Because it might make a huge difference in representing a large neural net inside your solution. So I think that is it for this episode. Hopefully, you guys understood, liked, and enjoyed it. And if you did, give me a thumbs up, subscribe to my channel, and I will see you in another episode. Until then, have a good one. Take care and bye bye.